Good Thursday afternoon, everyone. Welcome to lecture 17, Mathematics for Construction. What did we do last time? Lecture 16, matrices. We went through a lot of notes, basically reviewing CSEC matrices, right? Form 5. For some of you all, this might have been a long time ago. Talking about how to multiply matrices, how to add them. Addition and subtraction is the same thing, more or less. Identity matrices, determinants, the inverse, how to use the inverse, what a singular matrix is, how to solve simultaneous equations, linear equations, that is, simultaneous linear equations with matrices. Some equations you cannot solve using matrices, but when you can solve it with matrices, it's kind of short. You basically just have to know how to multiply two matrices and you could solve the simultaneous equations. So this is one of the nicest methods for solving linear simultaneous equations. Well, for two variables. For three variables and more, you need computers for that. Humans will take too long to use matrices to do those things, right? Finding inverses of a matrix and finding determinants, computationally expensive. Computers really like to do those things, to have better techniques to solve those kinds of things. So where we at? Course outline. Let's look at the course outline. We basically do all of this here. All the analytical methods, the trigonometry, the algebra, the matrices, LO2, forget that for now, LO3. We do the calculus, the integration, did some applications. LO4, we did trigonometry, vectors. Basically, it's a cosine rule, right? We did APs, and we'll do some dimensional analysis towards the end. What we head in towards really is LO2, which is statistical techniques, right? There's a lot of stuff here to learn, but if you look at the learning outcomes, apply statistical methods, calculation mean, standard deviation to produce appropriate solutions, right? Probabilities for binomial and normal. This will take a little while. These things are a little complicated. And hypothesis tests. We have some statistical stuff in a D1 up here. That's basically it too. So we heading towards statistics, right? So we'll start. What does the book say about statistics? Do we have anything lined up, right, in those topics? So let's try to get it. So, okay, there's the book here. What chapters we say we need to focus on? So we have some statistic here, 38, 37, 38, 39, 40. So let's check that out. So almost there. So we start off with 37 because we're gonna briefly scan through this here, right? Talking about statistics. We rather know every single thing. We're trying to just focus on what we need for your assignment, right? The things that are going to be on your assignment. So statistics, that's single page, right? So just briefly running through presentation of statistical data, okay? Statistics is really the science of, analyzing data, okay? And that's data and information, all these things have definitions, right? How you obtain data, right? We have methods, we could generate them ourselves, but we could measure other things and we get data. Data falls into different categories. We have discrete and continuous, right? Just going through some terminology here that you all need to know. Now, I'll outline the chapters for you, so I'm just doing a brief overview. These are the chapters you have to sit down and study. I'm not going to go into detail into everything, right? That work is for you to do. Classes for questions, right? So we talk about population, right? A sample that is selection from the population, right? We have things called frequency. So we have a set of numbers here. What's the frequency of each number? Number 2 occurs how many times? Number 7 occurs how many times? And so on, right? We have a relative frequency for different kinds of data that you could ask you. So this is really just introducing you to the idea of statistical thinking, where you have data and you want to analyze that data. We have certain metrics, certain things we like to look at first in the data to get an idea what the data is like, okay? Calculations are very important in statistics because you could do several calculations to give you an idea about some property in the data, okay? We will get to that in a while. So we have examples here of data. Data could be grouped or ungrouped, right? When you start to present data, sometimes you lose some of the information in the data. Raw data, is, these values, samples like this list here, 2, 3, 4, 5, right? That's raw data there. But when you put it in a chart, or a bar chart, or a bar graph, or something like that, or a pie chart, you kind of lose the data because you're looking at a summary of the data now. So just be mindful of that. Anytime you start presenting data, you depending on how you present it, you lose the data as well. We say ungrouped data. Ungrouped meaning we're not trying to put it in groupings or buckets. So think about, people's height. You measure the height of everybody in a classroom. You have 36 people in a classroom, measure the height of everybody. The raw data is the 36 data point values, 36 different heights. But then you could group them. You could say who is between 4 feet and 4.5 feet. And then who is between 4.5 feet and 5 feet, and then who is between 5 feet and 5.5 feet, and so on. You group the data. When you group the data like that, you lose the data because now you just have the groupings and you have a frequency count. You say, okay, 4 people between 5 feet and 5 feet 5, and 9 people between 5 feet 5 and 6 feet. You understand? You don't know what the actual data points are. You just know it have 6 people inside of there, or 9 people, or so on. So that's kind of what they're trying to show you here. Presenting data is very easy. It's very easy to present it. You just put this data in Excel and click 2 buttons and you present the data. This is not a hard thing to do. We need to get into the mathematics of it, not the diagrams or the art or the drawing. Those things are not complicated, right? The mathematics is what we need to look at. And as we all know, the mathematics starts to get difficult at some point in time. So this chapter shows you how to present data in different ways. This is more artistic expression on how to present data. You have no serious mathematics going on here, unless you call dividing by 100 and multiplying by a number serious mathematics, right? So I urge you to read through this chapter, understand the names of things, the terms, right? When you group in data, that's where you start to get frequency distributions. Because we don't know what the data points are. We have to count. We lose the data when you group the data, right? So we have bounds now. We have interquartile ranges and cumulative frequency distributions, right? It's important to understand these things. Not so much we're going to be doing it specifically, right? If somebody asks you to do a cumulative frequency chart, you just look up the relevant chapter in the textbook and group the data accordingly and then do the chart, right? Frequency distributions are very popular. Is a graphical representation of a tally diagram. You see how they group the data here? And they have the midpoints and they have the frequency. When you do this, you lose the data. This is the original raw data here. This grid here is this matrix kind of 81, 83, 87. When you group the data, you lose the data. I don't really know how many people had a score of 77. I just know, okay, 77 is between 76 and 78. It have 7 people in there. But I don't know what the actual scores are. I just know 7 people inside of it. Maybe 0 people have a class, you know, that score 77. Maybe all of 7 have the score 77. I don't know. You lose data when you present it. Okay. So frequency distributions typically you look like that. We have some examples here where they give you some data, measure it, and they give you a chart, draw the frequency distribution, calculate the midpoint, do a frequency polygon, right? Frequency polygon is just joining the midpoints of each of the bars together, right, on a histogram. Histograms are very peculiar because the area of a bar is proportional to the number of things in there, the frequency. So, you know, if all your bars are the same width, then you're looking at the height. The height is a measure. But I have histograms with different groupings, different widths. And therefore you use the area of of a bar to represent the frequency, right? That's getting a little bit too complicated. You don't need to go through all of that. This is a frequency polygon here. You're joining midpoints at each bar to each other and you get a polygon. Excel love to do these things for you all in 2 clicks, right? So a nice easy chapter focusing on how to present data. That is a chapter really you all should be reading on your own because I have no complicated mathematics inside it. We use in class time to get into the complicated mathematics, right? What is dispersion? What's this thing called dispersion? Measures of central tendency. So I'll take your time with this one, right? It's a single value which is represented of a set of values may be used to give an indication of the general size of it. So, you know, in everyday language, we use the term average. Okay, we say what's the average or something. Now that's a statistical term. However, we have different kinds of averages. We have different notions of an average, okay? Basic statistics. You have 3 notions of average: mean, the median, and the mode. Okay, an example of these things here. So if I have numbers 5, 6, 4, 5, 6, and 9, what's the arithmetic mean? Okay, what we call the mean. Well, you just add up the numbers and divide by the number of numbers. Okay, that's what the mean is. The median is the middle value. And if you have an even number of numbers, you just take the 2 middle numbers, add them and divide by 2. Okay. The mode is that measure of average. The mode is the thing that occurs the most. So we say we have a modal value of 5. If you have more than 2 values occurring the same number of times, you say it's bi or trimodal or multimodal. Okay. It's very easy, these things here. What people love is the idea of the mean value of a set of numbers. Given a set of numbers, find the mean. So look, they say find the mean, median, and modal value in these set of values. These floating point values here. We have 1, 2, 3, 4, 5, 6 numbers. So you add them up and divide by 6. That's the arithmetic mean or the classic idea of the average. The median value is you have to sort the numbers from left to right and pick the middle one. Okay, we have an even set of numbers. So you add the 2 middle values and divide by 2. Now the mean, the median value is not present in the data. That's something important to understand. 37.19 doesn't occur in the data. That's not a data point. That's a new value that is manufactured to give you an idea of something. That's not a value that occurs. Same thing with the mean value, the arithmetic mean. 37.2 doesn't occur here. Right? So they have these exercises here where they talk about this for discrete data. For group data, is a little bit different. What we do is we multiply the frequency, because group data, you don't have the data. Remember from before, with group data, you don't have the original data like this. You have it grouped together in a frequency distribution. So you have different groupings, and each grouping you have a frequency. You don't know what the actual values are, so you have to guess. So the guess is use the midpoint of the bar and multiply by the frequency. So that's why this fx thing here is happening. Okay. So okay, they have a frequency distribution of 48 resistors. Okay, so this is the breakdown here. Between this range here, we have 3. Between this range here, we have 10. And this range here, we have 11. And so on. When you add up 3, 13, 10, 9, 11, 2, you get 48. Okay? But we don't know what the actual resistors are. That's group data. All I know is I have 2 resistors with a resistance in this range here. I don't really know what the values are. You lose the data. So the only thing you could do is take the midpoint and multiply by the frequency. That's what they're doing here. This E looking thing here is called sigma, as a Greek letter, capital sigma, the Greek letter for adding things together. So you want to add up a bunch of things, we say sigma fx. And when you want to add up all the frequencies, you say sigma f. Okay? So, I mean, calculators could do this for you on Excel. Right? If you have it in tabular data, you multiply any frequency by the midpoint. See the midpoint values here. This is the midpoint at 20.5 to 20.9 is 20.7. They just add the 2 endpoints and divide by 2. So straightforward calculations for these things. Okay. Histograms. You could determine it from a histogram. These mean, median, and mode. You could determine it from a histogram, and that's what this diagram is showing you here. And they're very close together usually. Yeah? Usually mean, median, and mode, even if they have defined differently. And different calculations exist to find them. Different algorithms exist to find them. Sometimes in a group of data, they're very close together. Okay? We're not focused too much on histograms, finding median, mode, and things from histograms. This is what we want to get to here, because this is what in your learning outcome here, calculation mean and standard deviation, P3. That's what we're trying to get to. That's what this is here. Standard deviation is a concept in statistics, gives you a measure of the spread of the data. That will make sense to you in a while, right? Hopefully. But statistical thinking and even more difficult, probabilistic thinking is very different from algebraic thinking and geometrical thinking. So far we're doing mathematics, we've been thinking algebraically, you know, lots of x's and y's and x squared and equations. We've been thinking geometrically, right? We have a, you know, a triangle and you have to find the longest side or something like that. But statistical thinking is very different. And even harder than that is probabilistic thinking when we come to do probability. How those things work is very different from the mathematics you would have done before. So your mind have to adjust to that. You have to shape your mind and bend your mind to adjust to that new way of thinking. Okay? Standard deviation of a set of data gives an indication amount of dispersion or spread, how the data is scattered. So there's a value in engineering, root mean square value, right? Very, very popular metric to analyze a signal, root mean square, what we call RMS. Anybody who did any electrical stuff would know the RMS value of a current or a voltage or that kind of thing. It's really a measure of how it is distributed. A fluctuating signal varies, and an RMS value gives you an idea of how, you know, that the average value is. And is an average value that is useful, it turns out. Okay, that's what the standard deviation is. So you could give you an example with standard deviation here, how to calculate it. There's have different formulas for it, right? For grouped and ungrouped data, and we have some examples here. So this is what I would want you all to focus on, trying to find the standard deviation for both group and ungrouped data. right? So that motivate the idea of measures of dispersion, okay? Dispersion means how it spreads out, right? That's what the word, the connotation of the word is. So look at this 3 set of data here. The first data set, you have the number 7 5 times, right? Second data set, you have the numbers 5, 6, 7, 8, 9. Again, 5 numbers. And the last data set has 5 numbers. Negative 193, negative 93, 7, 107, 207. Okay. What is the mean? And when I say mean, you know, that arithmetic mean, which, you know, they showed you how to find I up here, you know, you add up all the numbers and you divide by the number of them, right? What's the mean of these 3 data sets here? If you could tell me that. So for part 1, the definition of mean, we write it as x bar, x with a horizontal straight line above it. It means the average. That's the notation for average, right? You see it here, x bar, right? In general, the mean of a set of numbers, you add up all the numbers and you divide by n. We write it as summation of x over n. So the book has it, call it x bar. Sigma is the capital Greek letter, means sum of, right? So this is a notation, sum of all the x's over n. This is essentially what it is. So that explains the notation I'm using here. If all the numbers are the same, the average is the number that is repeated. But the numbers 5, 6, 7, 8, 9, the average is still 7. And even these 5 numbers down here, the average is still 7. So all of them have the same average. But what is the difference among these groups of numbers here, even though they have the same average? What could you tell me about the groups of numbers? Anybody? So even though the average is the same for each of these sets of data, obviously the spread is different. The first data set has no spread. All the data points are the same, right? The second data set, 5, 6, 7, 8, 9, there is some spread in the data, but it's very little. The deviation is like 1 and 2 and so on, right? From the average. So the average is 7, but the deviation from the average is very little. But look at this one, the last one. The mean is 7, but where's the deviation from the mean? It's 200 in this direction and 200 in the next direction, right? There's a lot of spread happening here. How is this relevant in the real world? Okay, well, think about it. If you have a machine that fills bags of flour, right, with flour, right? So you have a machine, you calibrate it to fill a bag with a certain amount of flour in it. And you calibrate that machine to fill 7 pounds of flour. You have a 7-pound bag for flour. And the machine has to fill that bag with 7 pounds of flour. Now the machine dispenses flour, but it will have a little error in it. There must be some small error, deviation, right? If you package bags of flour and you take a sample, this is a quality assurance. So they'll say, okay, how much bags of flour did the machine package today? They say, well, okay, 100 bags of flour was made. So somebody will go and randomly select, say, 10 bags from the 100 bags and measure the amount of flour in each bag. And it better be close to 7, right? Because you don't want to be packaging flour and sending it out there and people getting 8 pounds of flour, but they're paying for 7 pounds. You know what I mean? So that machine better be accurate. Now, which machine would you like to have as a manufacturer who's packaging flour? Will you like a machine to package flour the way this first data point is here? All 5 bags have 7. Or will you want to have 5 bags of flour and the amount is 5, 6, 7, 8, 9? Or would you want to, you know, have a machine that packs flour, and this is what the amount of flour would be: 7 in one bag, 107 in the next bag, 207 in another bag. Which machine would you rather have as a business owner packaging flour? You want your machine to be like the last one or like the first one? Tell me. Obviously, number one. If I am selling flour, I don't want somebody to pay for 7 pounds of flour and I give them a bag with 207 pounds. You understand? That's a terrible machine. That machine has a huge deviation from the mean. The mean is supposed to be 7. The average is supposed to be 7. But what is my deviation from the mean on average? You see here? We're heading towards something different now. What is the average deviation from the mean? The mean is the average, you know, but I want to know what's the average deviation from it. Okay, and that is what this thing is here. Moving on to it here. That's what this concept is here, standard deviation. Standard deviation is a value, is a number, and that number is a measure on average how the other values of data deviates from the mean. The larger your standard deviation is, the larger your spread of data. The data is spread out from the mean a little bit more. So the standard deviation of this first set of data values here is 0 because it has no deviation. All the data points are 7. The mean is 7 and nothing deviates from 7. The standard deviation, the second set, is not 0. It's some small value, right? The standard deviation of the last data set is kind of big. Okay, the larger the standard deviation is, the more the data is spread out. And standard deviation, the number that you get back from this calculation here, gives you an idea of the standard deviation. And you have other things the standard deviation tells you. When we get to the normal distribution and probability density functions, you would see how important the standard deviation is. But it's a simple thing called the standard deviation. It tells you a lot about the distribution. Okay, so it's important to know how to calculate it. So hope that made sense. So there are different measures of the average deviation from the mean. Okay. Most useful one is the idea of the standard deviation. How you calculate it though? So again, we have a textbook, right? Shows us how to do it for discrete data and for group data. Remember, group data, you lose the data, but discrete data, you have all the data points. So, so again, the amount of scatter, dispersion, or deviation, right? That's what is the measure of. Root mean square value. So this is how it's obtained. So determine the measure of the central tendency, what the mean value is. So you have to find the mean first. Okay, that's part A. Part B, calculate the deviation of each member from the mean. So if you have like x1, x2, x3 is your data points, what is the deviation for each data point? Calculate those values, right? You have a finite number of values, so that shouldn't be too hard. And then square the deviations so that they don't cancel each other out, right, when you add them, because all will be positive. Sum them up, add them up, and then find the average of those, right? So when they say root mean square, is the standard deviation is the square root of the mean, right, of the deviation, the square, RMS, root mean square. Find the square root at the end. Square root of what? The mean of what? The squares. Root mean square, that's what it is. So that's standard deviation here. There's this formula here. So this is summation of all the squares of the deviations over n, and then you square root the final thing. X of x bar, of course, is the mean, which I have to calculate from the get-go, right? So the value of standard deviation gives an indication of the distance of each member is from the mean. So you have a set here, the mean value is 7, the standard deviation is about 4.2. This is a different set with the same mean, but the standard deviation is even less. So again, if you have a flour packing machine that is supposed to pack 7 pounds of flour in a bag, you wouldn't want your machine behaving like this, where one bag have 1 pound, a next bag have 4 pounds, a next bag have 10 pounds, right? That's not a good machine. Well, it's good for the customers, right? At least those who get more than 7. And these days, as flour going up, right? But if somebody pay for 7 pounds of flour and they get a bag with 4 pounds in it, I would imagine they'd be angry, right? But this is terrible here, but it's still better. 5, 6, 7, 8, 9. If I go in the grocery to buy a 7 pound bag of flour and I get a 6 pound bag of flour, that's a big difference. I could make some trouble for that. I want my 7 pounds of flour. I don't want no 6 pounds. Of course, if I get a 9 pound bag of flour, I just stay quiet, pay my money, and run out the store as fast as I could, right? Maybe, right? But I mean, who just go in the grocery with a scale? You know what I mean? But this machine here has the same average of 7. This machine here has the same average of 7. But we want the spread to be as minimal as possible. We want the standard deviation to be as less as possible. So this data set here has a standard deviation of 4.2. That's kind of bad. 4.2 is kind of bad. Depends on the data too. It depends on the data points. 4.2 could be very good. Okay. Standard deviation by itself don't make much sense. You have to still look back at the data. If I tell you standard deviation of something is 5, you don't know if that's good or bad. It's not like a absolute thing that you could look at. Oh, that's 7, that's bad. No. You have to still look back at the data. When we come to the distribution theory, you would see that, right? This data set here has a same average as 7, but the standard deviation is a lot smaller. So we know for sure that the standard deviation of this set is smaller than this set, but that still we're not sure if that's good or bad. You have to look at the actual data points. So let's look at a calculation. Determine standard deviation of this set of numbers. 5, 6, 8, 4, 10, 3. They want you to find the standard deviation of that. So, you get to working. First, you find the mean. What's the mean of that data? That's what you're seeing up here, right? Add up all the numbers and divide by 6. So the mean is 6. To find the standard deviation for each data point, we have 6 points here. We want to find the square of the difference between that data point and the mean. So we find 5 minus 6 squared, 6 minus 6 squared, 8 minus 6 squared, and so on. We will have 6 squared values. What we do is we need to add them up. That's what they did here. They add up all the squares of the differences. We have 6 of them. And then we find the average, right? 5.6. And then you have to square root that. So 2.3. So to correct 4 significant figures is 2.380. If you draw a table, it makes things a little bit easier to follow, right? To find the standard deviation. How about for group data? Well, group data, you don't have the actual values. You have a frequency and you have a range. Each range you have a frequency. So you multiply the frequency f by the midpoint of the frequency subtracted by the mean, right? So look at this data set here for group data, the way you find the standard deviation. The x values, we don't know what the actual x values here because it's group data. So you take the midpoint of each of the 6 ranges there. So your midpoint is 20.7, 21.2, 21.7, and so on. Take these 2 values here, add it and divide by 2. That's the midpoint. So you'll have 6 midpoint values, and you multiply the midpoint value, right? Sorry, the midpoint value, you subtract the mean from it, then you square that, and you'll get 6 different squared values. Then you find the average of that, then you find the square root. So it's a good bit of work. This is a good bit of work. You have calculators where you could plug in the raw values or the frequency distribution, and a calculator has a standard deviation key that would find it for you. But I mean, that's not very convincing to me that you know how to calculate standard deviation. So you ought to be able to do it on paper, okay? So we do some examples with standard deviation, how to calculate it, right? That will help us be able to do the standard deviation calculation in the assignment, right? So that's what this is here. And we could do some of the problems here in the textbook. And I could give you some as well, right? So let's see how that goes. So we take this example from the textbook. We know what the answer is, 4.6, right? So we have certain numbers. This is raw data, so it's ungrouped data. We want to find the standard deviation, right? That's what this question is about. So you have to find the mean first. What's the mean of these values here? That's what I mean by mean, or x bar. X bar is the mean, right? So you find that. And then this table might help you organize your data. So if you do a table like this in Excel, you could actually use Excel to help you do this, right? With formulas. So the idea is find x minus the mean after you find the mean. So you fill out this row here, right? With x minus mean. Then you square that and you fill out this row here with the square of the x minus mean, wherever the mean is here, you have to find. And then you could total to the bottom here what it is, which is what they say you have to do, right? You have to find the total of the deviations, the squares of the deviations from the mean. And then divide by 6. So after you do that, then you could find the standard deviation here. Forgot n here, but wow. So after this total here, this bottom right cell, when you finish it, you just divide that by n and find the square root. So the table would help you do your work in. And it's kind of easy to verify it in Excel as well. So do this now and finish it up. You know what the answer is supposed to be, 4.6, but let's see if we could get it, right? Character 3 significant figures. All right, so let's try to do this question here. How you find the mean? Let's find the mean. You add up all the numbers. And you divide by 6 it is. 1, 2, 3, 4, 5, 6, no, 7. Right? So take these numbers here. Ooh, I'm gonna copy paste this. Get more than a bargain forward. Could you all tell me what this sum is? What's the sum of all those numbers? No, the sum. No, not the average, the actual sum of the number. $196. All right. $196 over 7 is what? 28? Yeah, 28. Yeah. So this is the x bar is the mean, it's 28. So this is 35 minus 28, you know? This is 22 minus 28 and so on. 25 minus 28. Now we see the mean is an actual data point value. That will always be the case. So 30 minus 28 is 2. 33 minus 28 is 5. This is 0. This is what, negative 5. Negative 3. Negative 6. These values look right, guys. 35 minus 28 is 7. So this is 49, 36, 9, 25, 0, 25. We square in it, right? And 4. Then when you add up these values, what do you get? Right? 49 plus 36 plus 9 plus 25 plus 25 plus 4. I'm getting 148. Right? So the sum of the squares of the deviations is 40. So standard deviation should be square root of 148 over 7. So this is 4.598. If there want 3 significant figures, that is 4.60, right? Right? Before, because 598 rounded is 600, right? Right, 4.6, 4.6. So that's the correct answer. This didn't take long. I didn't find this took long, right? That's how you did. Frequency distributions is for group data, and there's a standard deviation for that. The formula is very similar. Multiply frequency by the square of the deviation of the mean from the midpoint of the interval. So I have to find the midpoint of the interval here for these. So there's a little more work, but it's the same thing. A table could help you, or you could just manually write it out on paper. It's fine. We're not going to talk too much about quartiles and percentiles, right? But you could read about this here. This is kind of self-explanatory. Where you divide the interval into quarters. You have an upper quartile, a lower quartile, and you know it doesn't have to be quarter. It could be any percent. You just divide by that. Okay. So it's very short. You see, it's very, very short here, the explanation they go for quartiles and so on. But again, this is more artistic stuff. This is not the mathematics, right? It helps you gain some insight into the distribution, but all cumulative distributions look like this here. It's like a stretched out kind of S, if you want. Think about it that way, right? What we have next? Ooh, probability. I think this is the topic that is give people the most trouble at a high level, not at a basic level. Basic level probability is fairly easy, but at a high level probability gets very, very complicated. Statistics is you have data, And you're trying to make sense of the data. So you get distributions and standard deviations and all these things. Right? Probability is the reverse, actually, where you hypothesize something and you calculate theoretically where's the chances of something happening, and from that you get data. So probability and statistics are two ends of the on a spectrum. Probability generates data. Statistics starts with data. Okay. So again, it makes sense, give you the notes. You don't have really much notes to do. Classes about doing calculations, right? So we're just gonna skim through what probability is. The given here is the likelihood of an event happening on a scale of 0 to 1. So if something cannot happen at all, the probability is 0. If something is most certainly going to happen, the probability is 1. And between 0 and 1, there's some fraction that tells you, a vulgar fraction, not an improper one. The fraction tells you the chances or likelihood of something happening. Okay, that's the intuitive notion of probability. Expectation, the chances of an event happening is saying a number of attempts is the probability of success in one attempt multiplied by the number of attempts. So I give you an example here. And a lot of the examples we're going to use a die or a pair or more dice, or maybe cards, like a standard pack of 52 playing cards, right? Where you take out the joker and all these things. Those are the examples you would tend to see in books, because generally most cultures know about dice and cards. Right? You don't have to be a card player, you just have to know what the composition of a deck of cards is. So if you roll a dice, or sorry, roll a die, okay, singular is die, you roll a die. You have 6 faces on a die because it's a cube. So the probability of any one number, if it's a fair die, is 1 over 6. Fair meaning each score has the same chances of happening. It is not biased, right? So it's a fair die. What's the probability of obtaining a 3 and upwards? Meaning a 3, 4, 5, 6. Okay, but that's 4 values there, right? So that's why we multiply it by 4, right? Because out of 6 possibilities, 3 and upwards is 4 of those. So that's 4, 6, which is 2/3. Expectation has to do with several events, right? One after the other. What's the chances of say, I roll a die 4 times? What's the chances of getting 2 6s and 4 tries? That kind of thing. The expectation will help you with that, right? Dependent events. Dependent events are events that, well, I mean, they depend on each other. The probability of one affects the other one, okay? Some interesting applications of probability deal with events that depend on each other. For example, if you're going to work, you might have 2 routes to get to work, right? If you take the first route, there's a chance that you will be late if you take the first route. But if you take a second route, there's a different chance that you will be late, you know? So you could say, you know, the chances of being late depends on the route taken. So you have 2 events there. Being late is one event, and taking a route is another event, and they depend on each other. Well, the being late depends on taking a route, not the other way around. Okay, so we have things like that in probability where an event, success or failure in one event affects success or failure in another event. So those events are dependent. Independent means they don't really affect each other, right? So it doesn't matter what happens in one event, the other event, the probabilities are unchanged. And the example is used here is if you're drawing balls from a bag and you cannot see the balls, right? You have green balls or red balls or whatever in a bag and you're picking balls. the chances of you picking a red ball the second time depends on where you pick the first time. So the color ball you get the first time affects the color ball you get the second time if you don't replace the ball. But if you're replacing, right? If you're replacing with replacement, you're replacing the balls, then what you draw the second time don't really affect what you drew the first time. Conditional probability is related to dependent events and is the chances of something happening given that something else happened. Right? So think of it in real words as like, what is the chances of reaching early to work given that it's a Friday? Some people like that. Some people is reach early to work all the days of the week except Friday. So the probability of reaching early to work, it changes based on the day. But we might want to quantify that. I might say, okay, given that it's Friday, what's the chance of you reaching early to work? That's a very different question from given that it's Monday, the first day of the week, what's the chances of reaching early to work? It might be larger because people might say, well, you know, it's Mondays, have more traffic. Let me leave earlier, so I might reach earlier to work. So the chances of you reaching late to work is much less on a Monday because, you know, you leave work early. But, you know, Friday, the week go on, you're tired, you can't wait till weekend. I'm gonna just leave whenever I could leave. I'm feeling fed up, you know, and you reach work late on a Friday. So that's maybe why the probability of reaching late to work depends on the day. And you might want to quantify that. And that's what conditional probability is about. When you start to get any mathematics of it, it's actually pretty simple, you know, probability at this level. It's not so bad because you're multiplying, subtracting, adding, dividing. It's arithmetic essentially. Well, what to divide by, what to subtract, what to add is not always clear. Where you have to multiply, where you have to add, how you have to multiply it, right? It's not always easy to figure that out. Something that confuses a lot of people is the or and rule in probability. Or means addition and means multiplication. So the addition law of probability, how we join two probabilities, okay? If the probability of one event A happening is P of A, and the probability of an next event B happening is P of B. Either any one of them happening, we add them. We say P of A plus P of B is the probability of A happening or B happening. Of course, provided they're mutually exclusive. If they're mutually exclusive means that they don't occur at the same time, right? So let me give you an example. You throw a die and you get a score of 4, right? That's one event. You throw a die and you get a score of 2. So somebody will be like, well, what is the probability of getting a 4 or a 2? Well, that's 1, 6 plus 1, 6, which is a third. Because those events are mutually exclusive. You can't throw a die and get a 4 and a 2 at the same time. They're mutually exclusive. These two events cannot occur at the same time. That's what mutual exclusion is. So you see, I have a lot of terms, independent, dependent, conditional, mutual exclusion, expectation. There's a lot of stuff. There's a lot of stuff to go through. Mathematically, the mathematics of it, the probability is not hard, but the thinking is difficult. Yeah, it's a different kind of thinking. As I said before, it's not algebraic thinking or arithmetic thinking or geometric or spatial reasoning or logic. It's not that kind of stuff. It's really probabilistic thinking, where you're thinking about the chances of something happening. What are your odds? What is better and what is worse? And some people have an knack for it. Some people just really struggle with it. Two events happening one after the other. That's what and is, right? That's how we join probabilities. So we multiplied probabilities when you say, what's the chances of A and B happening, right? So let's do some work problems on probability here. So you have a group of 20 men and 33 women. What's the chances that you select a person and it's a man, it's male? How you do that? Yeah, Dean is like the lotto, but lotto, lotto is a lot more complicated to calculate. But yes, his chances of getting something, you know. So what's the chance you get a man in a group of 20 men and 33 women? Well, the denominator is the total sample size, the set of all people, which is 20 plus 33, 53. But I have 20 men, so the chances of getting a guy is just 20 out of the 53 chance. That's basically, that's what it is. Now, probability don't mean it's going to happen. Probability is not trying to tell you, if I pick a person, I will get a man. No, it says the chances of getting a male in this group is 20 out of 53. It's a little less than 0.4, right? If you select a woman, there's a higher chance because more people in the group are women. So this should make sense to you, this example here. Was there some other examples here? Now, it's important to understand that when the total probability is always 1. So if you throw a die, what's the chance of getting an even number? That's if we call that P of A, then P of not A, which is the chance you didn't get an even number. That's just 1 minus the probability you get an even number. So that's what they're trying to show here. The total probability is always 1. The probability of an event happening plus the probability of that event not happening, it adds up to 1. And we could use that to solve problems. Later on, you could use that to solve problems, that notion. So expectation is the average occurrence of an event in a number of attempts. So it's like, how many times you reach late to work this week? What's the expectation that you're going to reach late this week? What's the number of days late you're going to reach this week in work? You could calculate that, yeah, if you look at your past data. You have 5 working days in a week, right? Some people, the expectation that they reach late is 5, you know. All 5 days they're going to reach late. Some people, the expectation is 0, right? It's so small. You could almost say they're not going to reach late because they're always early. What you do, the probability of reaching late, you multiply that by the number of times, and that would give you an idea of the average. That's the idea of the average, you know. Expectation is really average, the weighted mean, the arithmetic mean of a bunch of events happening, right? So if 3 attempts are made to throw a die, obtaining a 4 and upwards is 3 by 1 over 6, right? Which is a half. So look at this example here. You have 10 horses in a race. What's the chance that a horse wins the race? Like, pick one of the horses. What's the chance that he wins the race? It's 1 out of 10. That's simple enough. Look at this one now. The running horses in both the first and the second races. You have 10 horses in each race. Now, the question I ask yourself, does the outcome of the first race affect the outcome of the second race? So you're asking yourself if the independent events. We know they're mutually exclusive. 2 races can happen at the same time, right? Because the 10 horses can be in 2 different races at the same time. You have one race, and when that race finishes, you have an next race. So you know we're mutually exclusive, these events. But independent means does one affect the other? And the answer is no. The first race, the outcome of the first race don't affect the outcome of the second race, usually, right? So the probability of selecting winning horses, first and second race, you have to multiply the events because it's and. It's not or. That's why we have 1 over 100 here. You could think of it differently, you know, in the sense that when you have 2 races, how much different possibilities for winners you could have for those 2 events. You have 10 horses in position 1 and 10 horses in position 2. If you have the two positions, how much possibilities you could have? You have 1, 1, 1, 2, 1, 3, 1, 4 up to 110, and 2, 1, 2, 2, 2, 3, right? You have 10 possibilities for the first winner. And for each of the first winner, you have 10 possibilities for the second winner. That's why 10, 10 is 100. That's why I have 100 possibilities in all. Right? And out of all of them, right, selecting a winning horse in the first race, that's just one choice in the first race and one choice in the second one. When we multiply that, we still get one. So it's 1 over 100. It's a very small chance that you get the winners for both races. Okay. Lots more examples for this here. So the idea of a possibility space is a set of all possible outcomes in an experiment or event. We use these terms event or experiment. It just means a situation that can have many outcomes. Right? Each possible outcome is a sample point, and the set of all sample points is called the possibility space, and is given a letter capital S. If the possibility space is finite, for example, if you roll a die, there's a finite number of possibilities you could have, 6 of them, right? When you roll a die, be denoted by n of s, n brackets s. That's the number of points in that space, the total number of points. The classic definition of probability means dividing the number of times event A could happen over the total number of possibilities, n of s. So total possibility space, the number of points, is the denominator. The numerator is the number from that total list that has the event occurring. Okay. A bar is the event A does not occur, meaning not, right? The opposite. Those probabilities add up to 1. So I have this question here. You're playing a certain game and you're allowed 2 options to win a sum of money. So take a single die, roll it, and obtain a score of 4. If you get a score of 4, you get the sum of money. Or you could choose to roll 2 dice, and whatever the score is on the 2 dice, you add it up. If that score is 8, then you would get the same sum of money. Question is, which option would you use to play the game and why? Okay, think about it. So option 1. So let's deal with the traditional definition of probability, right? First of all, what is the possibility space? The first option, right? The possibility space is the set of all different scores you could get, right? When you throw one die, what are the possible scores you could get? So you could get 1, 2, 3, 4, 5, 6. That's the possibility space. The first option. So n of s equals 6, right? Because that's the number of items in the possibility space. That's what they say, number of points. Ooh, hold on. Number of points, right? That's what NS is. So I could say here, after this, let A be the event, A4 occurs, then N of A, number of times it could get a 4 is 1, right? So probability of A occurs is 1/6. That's option 1. So this is the conclusion. The chances of you winning the sum of money is 1/6, right? Option 2. We can represent a single outcome as an ordered pair of scores. So the first score is the score so how much outcomes you have, right? What's the possibility space? So I could represent the scores as ordered pairs. So I could say 1,1. It means I get a 1 on the first die and a 1 on the second die. What's another possibility? 1,2. 1,3. 1,4. 1,5. 1,6. So these 6 outcomes here are the 6 possible outcomes when the first die has a score of 1 on it. So if the first die has a score of 1, the second die could have a score of 1, 2, 3, 4, 5, or 6. But that's just for the first die having a score of 1. What about if the, what about if the first die has a score of 2? So we could have 2, 1, then 2, 2, then 2, 3, and so on up to 6, 6. How many ordered pairs are these inside of here? We have 6. So this is the justification of the possibility space. We have 36 possible outcomes. The first die has 6 scores possible. But for each of those 6 scores, on the first die, I have 6 scores on the second die I could get. So it's 36 possibilities in all. How much of these possibilities result in a sum score of 8? Let B be the event. The sum of the scores on the 2 dice is 8. How much ways you could get a score of 8? So the space for B, you could represent B as a space in a sense. So could I get 8 with a score at the first die as 1? No, because you need 1 and 7. But I could get 2 and a 6. I could get a 3 and a 5. I could get a 4 and a 4. I could get a 5 and a 3. And I could get a 6 and a 2. These are the combinations that allow me to get a score of 8 when I throw 2 dice. So, you know. So N of A is 5. So probability of B occurring is N of B over N of S. And that is, as Renson says, 5 over 36. And 1/6 is 6 over 36. So 5 over 36 is less than 6 over 36. So we could say the probability right? So this is interesting here, right? The probability of scoring an 8 with 2 dice is actually less. Is a less likelihood of that happening. 1 over 36 less than this one. Scoring a 4 with 1 die. Okay, so option 2 is not the better one, is actually less. Your chances are better. Just take 1 die and try to get a 4. It's actually better than taking 2 die and trying to get a sum of 8. So I will use the classical definition of probability here. Just sit down and think about the sample size, the possibility space. And you would see it has some counting techniques here. And you know, the book covers permutations and combinations towards the end, right? So we have some problems with probability here. We talk about with replacement, without replacement. You could look into that, right? So you read this book, read these questions, you try to figure out what they're doing and how they're thinking about the problem, right? you could draw diagrams to represent things, but you see, eventually they come to permutations and combinations. This is very complicated. These counting techniques. This is a topic called combinatorics, one of the hardest branches of mathematics in a university maths department, right? Combinatorics is a rough specialism, right? What is a permutation? What is a combination? So I want you all to read this for next class. Next class, we're going to talk a little bit about this. And this will help us to count the possible number of things happening so we could get the right denominator here, n of s, and maybe the right numerator as well. It is not always easy, these probability problems. Okay, so I want you to read this chapter, and for next class, we'll continue with perms and combs, permutations and combinations, to make sure we understand what this probability thing is about before we move on to the binomial distribution. There's a discrete probability distribution that there's a formula that generates the probability of different events happening. We'll talk about what a probability distribution is. Before we reach there, we need to understand basic probability. So I suggest you all read chapter 39, at least chapter 39 properly, and try the questions in it.